Hello, students. In this particular video, we're going to go over the concepts of nomenclature. Basically, nomenclature is how do we name compounds and elements, and also how do we express them? How do we write them out, which is typically referred to as a molecular formula. Now, in this picture, we have some sugar. And here you see the space-filling model trying to represent that sugar molecule. Typically in a reaction, you would write out its molecular formula. So you would write C12H22O11 because it's table sugar, which is sucrose. And there's 12 carbons, 22 hydrogens, and 11 oxygens. And then you would write a subscript S. And the reason why you write that subscript S is because it's a solid. And then here they're blowing up the tip of this pencil, and that is graphite. Now, graphite is just carbon. And that has a subscript S because it is also found as a solid at room temperature. The difference is the sucrose is more than one type of atom. It isn't a fixed ratio, right? And it's a specific unit, so we call that a compound. Carbon, by itself, the graphite, is just one type of atom, so that's considered an element. Another example of a compound, other than sucrose, is not just table sugar, but table salt, which we know as sodium chloride. And we would just write a little lowercase subscript s to show that it's a solid at room temperature. So this is pretty much what we'll be introducing in this video, and then following this video, we'll talk about the different types of compounds and how to name them appropriately. So the first thing, when elements form compounds, their properties completely change. I talked about this in an earlier video with the octet rule, but I'd just like to review it again. So here I have sodium. It's a volatile, right? A very reactive solid. If you throw it in water, it'll literally explode. It oxidizes quickly. So it's an extremely reactive metal in nature. Here is chlorine, a brown, noxious gas, right? You don't want to inhale this stuff. But when they combine, they form table salt. And you consume this, and actually you need salt as part of your electrolytes in your body. So one of the things you need to realize is that when elements combine, their properties change. Okay, so salt is very different from the individual elements of sodium and chlorine. So this under here is how we would express this reaction, right, on paper. So we have to write it and symbolize it and use it as a model somehow. So what do we write? We write molecular formulas. So here we have sodium. How do I know sodium's Na? Well, because you're learning, the periodic table, and you're knowing at least the first 20 elements. And sodium, right, it is atomic number 11, right? So it's in period 3, group 1A. By the way, if you don't have a periodic table, go ahead and grab that. It'll really help you. And we know it's a metal because it's on the left side of the periodic table, and it's found in nature as a solid. So that is an element, and this has a neutral charge. Why does it have a neutral charge? Well, there's 11 protons and 11 electrons. So now we have chlorine. Chlorine is also an element. It's a non-metal because it's found on the left side of the staircase. And we also realize that it's an element because there's only one type of atom. Now we do notice that there's this subscript of 2. That's because this particular element is a diatomic, and this video will discuss that as well. We have the subscripts, or the subscript G here, to represent that it's a gas in nature. And then the arrow is showing that when these reactants, because that's what these are, they're reactants, when they come together and form new bonds, they produce table salt. sodium chloride, which again is a solid at room temperature. So typically you have your reactants on the left, you have an arrow, and there are your products. This is the ending material, what has combined to make something new. Now, when I look at this equation, you might notice that it's not balanced, right? On the reactant side, there's 2 chlorine, but on the products, there's only 1. So what I have to do is balance it. And I balance that by using coefficients. What I do not want to do is change the formula of sodium chloride because that is not the correct formula. So I have to balance the number of atoms on each side because we have to obey the law of conservation of mass. You can't create or destroy it. I balance it by using what are called coefficients. So I have to put a 2 in front of the molecular formula of sodium chloride. This video is not about balancing. We do this in later chapters, but I'm just making it consistent and make sense. So I put a 2 in front because now I have 2 sodium chloride. So basically I can think of it as 2 units of sodium chloride, and there's a total of 2 chlorines, just like there is on this side. But now that I put a 2 in front, I also have 2 sodiums. So what do I need to do to balance it on the reactant side? I have to put a 2 in front of the sodium on the reactant side. So now both sides have 2 sodiums and 2 chlorines atoms. So what we just did is we used chemical formulas to refer to compounds. It's a lot easier to just write out chemical formulas. So it's a way to represent the number of each element and the elements involved either as atoms or compounds. So the most common is the molecular formula, which is pretty much what I was writing out there. But there are 3 types of formulas when we discuss formulas. So one type is the molecular formula. This would actually give you the number of atoms in this element or this compound, this molecule. So H2O2 is hydrogen peroxide. Now there is something different than the molecular formula. It's referred to as an empirical formula. The empirical formula, really you can consider it the simplest formula. You can consider it the reduced ratio. So when I look at hydrogen peroxide, I have the subscript 2 for both hydrogen and oxygen. So really I could divide both of those by 2 and simplify it, and I would get an HO. That's what the empirical formula is. It's the simplest formula for a molecular formula. So the structural formula actually tries to draw out the molecule by using lines. The lines represent bonds. So for hydrogen peroxide, it'd be drawn like that. So we would see that, oh, okay, this molecule, it actually has 2 oxygen and 2 hydrogen. That's why because it's a molecule, the molecular formula is H2O2 and not just HO. So here we have benzene, and I could even count, whoa, there's a, this is the structural formula, but I could count out and write out the molecular formula. There's 1, 2, 3, 4, 5, 6 carbon, and each carbon has a hydrogen, so there's 6 hydrogens. So that would be the molecular formula. And then here I have the molecule, right? Acetylene. Now, this is, or ethine, this is a little bit different, right? So in this structure of benzene, we see single bonds and a couple of double bonds, right? And ethine, we see a triple bond and a couple of single. We'll get into that later. Don't worry too much. Right now, we're just looking at structures and writing out their molecular formula. So for this ethine, there's how many carbons? 2 carbons, and there's 2 hydrogens, right? Here's what's interesting. Both benzene and ethine have the same empirical formula, CH. They have a 1-to-1 ratio of carbons to hydrogen, just like the hydrogen peroxide does for hydrogen and oxygen. But because it's a molecule, we want to represent the actual number of atoms, okay? Now we could even, get more sophisticated models. So we talked about the molecular formula, and the structural formula shows the lines as bonds, but there's the ball and stick model. So if you ever get a molecular model kit, you would put these together and you would see that the carbon is black and the hydrogens are white. And it would show the bond angles and the molecular geometry. And then the space filling model, it's a little bit better because it doesn't show these long lines that represent the bonds. It just shows how compact this would be. So that's another example of models representing compounds. So this particular compound is methane. And you don't need to know methane as far as nomenclature, how to name it. We don't do organic in this class. But for the most part, it's just good to get comfortable with that. Now, how do we write out these molecular formulas? Well, typically you're going to write out the more metallic element first. So the further you are from the upper corner, the more metallic you are on a periodic table. So as you go across this way, right to left and down, you're more metallic. Okay, and remember, sodium's over here, chlorine's over here on the periodic table, and that's why we write the sodium before the chlorine in sodium chloride, because we write the more metallic element first. That's why the organization of the periodic table is so useful, and you don't have to memorize it. It's a cheat sheet. Whatever's on the left, remember the staircase, right? Whatever's over here is a metal. What's on the right is a non-metal. We use the subscripts to indicate the ratios. So in CH4, we use the subscript 4 because in that compound of methane, there were 4 hydrogens to 1 carbon. So why is that important? Well, you got to represent the right molecule. You got to represent the right structure. So you need not just the elemental symbols, but you need the subscripts. Now, if there's a group of atoms that travel together, we'll use parentheses to show that group. So water. Everybody knows water is H2O. Well, what do? We write the elemental symbol for hydrogen, which is just a capital H, and there's 2 hydrogens per oxygen. What's the elemental symbol of oxygen? It's O, capital O. So why do we have a 2 there? Because it's H2O. Really, we could think of the water molecule as an oxygen bound, and I'm drawing lines to show the bonds, right? I'm drawing lines here to show 1 water molecule. So per 1 water molecule, there's 2 hydrogens, right? And there's 1 oxygen. So I have to use a subscript 2 to show that there's 2 hydrogen atoms. Well, what if I had something like magnesium nitrate? Now, there's a lot of boxes here. Don't get confused, but magnesium nitrate. Nitrate is a group, okay? It has a negative charge. Magnesium, if I was to look on the periodic table, magnesium is in group 2, right? So as I go down the periodic table, down a column, down a family, down a group, it's in group 2, or I prefer saying 2A. So that means magnesium tends to form a 2+ charge. Now, with atoms, and magnesium's right here is not an atom, it's an ion, but atoms and compounds are neutral. So how do I get magnesium as an ion with a 2+ charge and nitrate, which has as a group a negative charge? How do I get these 2 ions to form a neutral compound where there is no charge? You do what I call a crisscross. You take that number, you put it over here. You take that number, you put it over here. Well, there's really just a 1 for the nitrate. So we only have 1 magnesium, but we have 2 nitrates. That's why we use that subscript 2. We need 2 nitrates to cancel out the 2+. And if you don't like doing it the way I just showed you with the crisscross, you could just say, all right, well, Magnesium's 2 plus. I need, you know, a 1 negative and another 1 negative. Whoops, sorry, I just made the subscript in nitrate a superscript. I need another 1 negative to cancel out that 2 positive, so this species as a whole has a neutral charge. So why are formulas so useful? Well, because when we look at things at the macroscopic level, we have to represent what it is at a molecular level. So how do we do that? Well, in this glass of water, right? If we magnified it, right, this is basically a pure substance. We'll assume that it has no salt, right? We didn't get tap water, we got distilled or deionized water. It's just a bunch of what? Water molecules. It's a bunch of H2Os, right? And they represent the hydrogens as white and the oxygen as red. So it's just this compound of H2O, water, right? So this found in nature, water's a liquid. When I write this, I basically mean this compound. And this compound is plural. There's many water molecules. The singular of the compound would be this molecule of H2O. So how do we write it? We just write H2O to represent that compound in the correct ratio. So in the earlier video, we talked about matter. There's pure substances that have fixed ratios, and there's mixtures that do not. So the first thing we did when we talked about matter is we kind of went to the elements and discussed atomic structure. The reason why we talked about atomic structure is an element, if you look at a periodic table, it's a periodic table of elements. So when we say copper, and copper is a solid, why? It's a metal. So at room temperature is a solid. When I take a pure copper rod, that is the plural of the singular of an atom. So it's just a bunch of copper atoms hooked up together. So when we're naming things, we're going to focus our lecture, now that we understand atoms and atomic structure, we're going to focus on this part of matter. We'll get to mixtures in later chapters, but right now, we're going to look at matter and we're going to focus on pure substances. So pure substance is composed of one type of atom or molecule. So copper is an element. Why? There's only one type of atom, the copper atom. Sucrose, which I wrote earlier on the slides as C12H22O11, it's more than one type of atom, but it's bonded in a fixed ratio. So it makes a compound. So in this case, sucrose, the compound of sucrose, the individual units are molecules. And I want to remind everybody that atoms and molecules, or atoms and compounds, have a zero charge. So that's what we're going to focus on. How do we name pure substances? How do we name elements and compounds? And now we have to further break down these elements and compounds into what is an element and what is a compound. So again, an element is one type of atom, but it can get tricky. Why? Well, you have what are referred to as atomic elements, like neon, where there's just a bunch of neon atoms not bound together. And this represents a gas. That's why the particles are so far apart. So in a reaction, we would just write NEG, but neon's unreactive, so it wouldn't be involved in reaction. But for the most part, it's just a bunch of singular atoms separated. But I can have an element that, I don't like the term molecular, right? It's still an element, and it's still one type of atom, right? But now the atoms are not just by themselves. So in the example of oxygen, we have the subscript 2 because we have two oxygens hooked up together. So it's an element because it's only one type of atom, right? It's only oxygen. Yes, there are two of them hooked up together, but it's only one type of atom. So it's an element. I could look on the periodic table and find that elemental symbol. Now, compounds are different than elements because they're more than one type of atom. They're in a fixed ratio, right? But there's more than one type of atom. So a lot of times they use the term molecular. I call these covalent compounds, okay? Your covalent compounds are your nonmetals bound together. So the nonmetals are on the left side. There is an exception, hydrogen. But both hydrogen and oxygen are nonmetals. When they combine in a 2-to-1 ratio, you form water. And we represent water as H2O. Now, molecular compounds, which I'm going to call covalent, the reason why they call them molecular is because they actually form singular individual molecules. The other type of compound also has a fixed ratio. So the example I was writing was sodium chloride. And the ratio is 1 chloride ion to 1 sodium ion. But it is a formula ratio. It's a simple ratio. It's actually, with ionic compounds, there is no individual molecules. They have these complex repeating lattice crystal structures. But really what the formula is representing is the correct ratio for that compound. It's still a compound. Why is it still a compound? Because it has more than one type of atom in a fixed ratio. So that is the key. Elements, one type of atom. Compounds, 2 or more. And now we're going to talk a little bit about, what are some examples? So atomic elements, liquid mercury, it's atomic. Why? It's just a bunch of mercury atoms right next to each other through metallic bonding. So how would we write that in a reaction? Or just if I wanted to write the mercury as a symbol, Hg, and I actually put an L there because it's actually one of 2 of the elements that's found in nature as a liquid. Well, what are example of the molecular elements? Again, I didn't like this because I don't like that. But there are elements where there's more than just one atom by itself. So we saw oxygen and we wrote it as O2. Well, here is chlorine. Chlorine gas is written as Cl2. Why? There's 2 of them. So typically they're named molecular. I'm just going to call them diatomic for now. Diatomic means 2. There are more than diatomic elements. So examples, phosphorus, there's 4 and it forms a solid. You go to sulfur, there's 8, it's a solid. Selenium, there's 8, it's a solid. If you don't know those, that's fine. Don't worry about those right now. I'm just introducing. But I do want you to know the diatomics. And you know a lot of them. I mean, oxygen, chlorine. I bet you know more. But a lot of people get nervous because they start thinking, this is when I got to start memorizing all this information. And the way I teach, I don't want you to have to write out 1,000 3x5 cards and drill thousands of those. It just takes too long. So we're going to use little tricks. So there's 7 diatomics, okay? And I use silly little things to help me remember. It was the only way I could remember. So what I use is Sir Brinkelhoff. Now, Brinkelhoff. What I want to show you is if you get a periodic table out, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine, they all form diatomics in nature. So when I say oxygen, I mean O2. Oxygen will never be alone. It will never be by itself. So if I had pure oxygen as an element, it's O2 because it's one of the diatomics. So how can you remember it? Sir Brinkelhoff. Now there's other acronyms that people remember and you could totally use it. I don't know why this one stuck with me in college. It was probably because I was goofy and I said, well, Sir Brinkelhoff, he drinks 2-fisted. He has a beer in each hand, so he has 2. Sir Brinkelhoff, you can't drink him under the table. Now, again, that's my goofy way of remembering it. If you don't like it, totally cool. You don't have to like what I like. Some of you might like the periodic table. So there's another way. Sir Brinkelhoff, we got iodine, bromine, chlorine, fluorine, oxygen, nitrogen. Oh, whoa, this looks like a 7. So if you look on the periodic table, there's a 7 right there. The problem is there's only 1, 2, 3, 4, 5, 6 of the 7 diatomics. Well, you can think of it as the 7's pointing towards the 7th, the hydrogen. Okay. You can memorize it however you want. And if you want to throw it on a 3x5 card, that's totally cool. I just remember Sir Brinkelhoff. What about covalent compounds? Well, CO2, what is that? That's the molecular formula, right? That's the formula. What do we have in here? We have that space-filled model that we talked about, right? What's this? This is the structural model or structural formula where we're using lines to show the bonds. What's that? Oh, that's the ball and stick model, right? So the blacks representing the carbon, the reds representing the oxygen. So again, there's many ways to express these compounds, but really CO2, well, this is dry ice. It'll sublimate and go from a solid to a gas. So typically we find CO2 in nature as a gas, but if you ever bought one of those delicious Baskin Robbins 31 flavors, you know, ice cream cakes that I love. So if you ever want to buy me, no, I'm joking. But those Baskin Robbins 31 flavors, if you buy those cakes, they sometimes give you dry ice to keep that cake cool. And then, you know, if you had kids, you threw it in punch on Halloween and it would bubble and look like a witch's brew. Anyways, I digress. So CO2 is really a covalent compound. It's molecular. How do I know it's covalent? This is what I want you to know about covalent compounds. They're nonmetals. So covalent compounds are nonmetals with other nonmetals. Both carbon and oxygen are nonmetals. How do I know that? Periodic table, the best cheat sheet in the world. It's on the right side of that staircase. So they're both on the right side. They're both nonmetals. So nonmetal must mean they're covalent. They're molecular. Well, what about ionic compounds? Ionic compounds are different. They're metals with nonmetals. Now, how am I going to know that? Periodic table. You're going to get your periodic table. To the left of the staircase, metals. To the right, nonmetals. So what are ionic compounds? Well, they're compounds that have charged particles, which we called ions. And there are cations and anions. If you don't remember going over this, it's in the video, right, for ion formation. You should review that video, okay? It's assumed that you already have done that, but go over ion formation. So when I say sodium chloride, again, this is my molecular formula, and really it's showing me my ratio of sodium ions to chloride. Realize there's no molecule. It's a repeating lattice structure that forms these beautiful little salt crystals. So we refer to the molecular formula for ionic compounds as formula units. The reason why we do that is there's really no molecule here. So it's typically referred to as a formula unit. Now, what you have to understand is this ratio for this compound. Again, sodium chloride is a compound because we have two, right? We have two types of elements together in a fixed ratio. That's why it's a compound. Why is it an ionic compound? Well, it's ionic because it has a metal, the sodium's a metal, and it has a nonmetal, the chloride. You have to realize, even though these ions separately have charges, when they come together, they form a neutral compound. So I want to emphasize atoms, so elements, compounds are neutral. They are neutral. Ions aren't, but ions come together in a certain ratio, right? Sodium has a plus charge, chloride has a negative. When they come 1-to-1 ratio, the positive and the negative charge cancel each other. And again, where can you review this? Ion formation video. Or, whoa, look at that, like magic, the periodic table, right? So we talk about how in group 1A, right, they have a choice. Everybody wants to be nobility. Everyone wants to be a noble gas. So let's say you want to be like helium or neon or argon or, I'm not going to go all the way down, but everybody wants to be one of those. So here I have sodium, right? Who does he want to be like? Wants to be like either argon or neon, right? What's going to be easier? Well, sodium has 11 protons, and I could look at the periodic table, and that number 11 is the atomic number of the number of protons, and it has 11 electrons. So it has a choice. It could be like neon, right, which has 10 electrons, or it could be like argon, which has 18 electrons, because neutral elements have the same number of protons and electrons. So sodium could try to go from 11 electrons to 18, steal 7, too hard, or lose 1. So what does it do? It gives away 1 electron. And when it does that, what's left? Well, I still have 11 protons in the nucleus, but now I only have 10 electrons orbiting around this nucleus. Well, now I don't have a 1-to-1 ratio between protons and electrons. So 11 minus 10 gives me a +1 charge. Oh, I have a charge. I'm an ion. What charge did sodium form as an ion? +1. Why? Because it's in group 1. Group 2, same thing with magnesium. I could try to be like argon, but I'd have to gain how many electrons? 1, 2, 3, 4, 5, 6. Or I could just lose 1, 2, and be like neon. So if you're unfamiliar with this, again, you want to go back to the ion formation video where I talk about this. But then when we go to the non-metals, unlike the metals, which are really far away and have to steal a lot of electrons, the non-metals are right next to the noble gases. So for fluorine, right, is it easier to gain 1 electron or lose, because it has 7 valence electrons, that's why it's group 7A, lose 7 electrons? It's easier to gain 1. So it gets 1 electron. Who does it get it from? Whoever's willing to give it. I mean, if there's a sodium around, sodium will give it to fluorine. So I'll do a really quick predicting ion formation review, but you really need to go to that video if you don't get this. And then the next video you should watch after this is how to name ionic compounds. So basically, if you lose an electron, so if you lose an electron, you're going to lose negativity, you're going to become positive. That's called a cation. Why? Cat, paw, positive. So here I have potassium. It's in group 1A. You're looking at your periodic table. The first column, 1A, what does it do? It'd rather lose 1 electron and become like argon than try to steal all those other electrons to be like krypton. So that's what it does. It goes from 19 protons and 19 electrons to 19 protons and 18 electrons like argon. And then there's the 1 electron that it loses. So just remember that. 1A plus 1 charge, 2A plus 2, 3A plus 3. Okay, now 4A, they don't have anything. So carbon is unique. It's like right in the middle. It wants to form that octet like the noble gases. So it could lose 4, right? It could lose 1, 2, 3, 4 and be like helium, or gain 4. So really carbon could have a +4 or a -4, but it tends not to form ions. So it doesn't do that. And we're looking about ions. But if I look at nitrogen, I only need to gain 1, 2, 3. I'm not going to lose 5 when I could just gain 3. So when I gain the electrons, I become negative. Oxygen, 1, 2. So it needs 2 electrons. Chlorine, 1. So it forms a -1. So how do I know if something forms a negative charge? Well, when you gain negativity, and that's what an electron is, you become negative. And that's not a cation because it's not positive, it's an anion. So we look at chlorine, right? Chlorine has 17 protons and 17 electrons. If I add one more electron, what do I end up getting? I get 17 protons and 18 electrons. What's 17 minus 18? Isn't that a -1? Yeah, of course it is. That's why it has a -1 charge. And it's charged because it's an ion. But again, do you have to memorize any of this? Nope. Like magic. The periodic table is your friend. So I'm glad you guys watched this video. I hope you hung in there. Thanks for watching. Now, after watching this video, it'd be great to go to the next video where I talk about how do I name binary ionic compounds. Thanks so much for watching. See you in the next video.